dear students of class 11. Today we will be continuing with the isomerism. So in our previous video we have discussed about types of isomerism. Broadly it is classified into structural isomerism and stereoisomerism, and we have discussed about different types of structural isomerism. Today we will be discussing about stereoisomerism. So stereoisomerism are those compounds which have same molecular formula, but they have different arrangement of atoms in the space. Now, let me give you an example. See, whenever different groups are arranged around a central carbon atom, and if these attached groups they vary in their position in the space, then that will give rise to stereoisomerism. For example, see, suppose you have a carbon center and this is attached to say 4 different groups. 4 different groups. Now, in this case, you can see A is here up, B on the left hand side, C is below carbon, and D is on the right hand side. Now, these positions of these different groups, now if they vary in their position in the space, then that will give rise to stereoisomerism. For example, now instead of having A up there, you can have D here, you can have say C, you can have A here, and suppose you can have D here. Then you can see that they have its molecular formula. Its molecular formula is same, that is C along with A, B, C and D. This is the carbon center and this is the attached group. This small c is the group which is attached to the carbon. Now with the same molecular formula, you can have this structure or you could also have this structure. Now these two different structures arises because of what? Because of their positions, their different position in this molecule, and the positions of these different groups here in this particular molecule is again different. Now such types of isomerism is known as what? Stereoisomerism. So let's discuss in more detail about stereoisomerism. Stereoisomerism is further classified into conformational isomerism and configurational isomerism. Now, you can refer to page number 12.40 in your book. Page number 12.40. Refer to this page number. Now, I told you stereoisomerism is classified into 2 types. Again, this stereoisomerism is classified into 2 types. One is conformational isomerism. The other one is configurational isomerism. Now, in case of conformational isomerism, same molecular formula, different structures. Now here, these structures are free to rotate. These different groups which are attached to carbon are free to rotate around the sigma bond. Now this conformational isomerism takes place in compounds which has sigma bond only. That means single bond. And in single bond, free rotation is possible. Free rotation is possible. Okay, so you have to remember this much for conformational isomerism. So conformational isomerism takes place in compounds which has sigma bond. Sigma bond means compounds having only single bond, and whenever you have single bond, then free rotation around the carbon atom of these different groups is possible, and because of it you get different stereoisomerism and in particular conformational isomerism. Now whenever you come to configurational isomerism, here presence of double bond is must. So here what you have double bond is present, and because of this double bond there is restricted rotation. Restricted you have what? Again, this will be again classified into two different types. Conformational isomers are the stereoisomers that cannot be interconverted simply by rotation around sigma bond. Okay? Now, this conformational isomerism, in this case, see, the most important part is what? There is a restricted rotation. Now, this restricted rotation could be because of double bond or presence of other bulky groups, because of which they cannot rotate throughout, say, 180 degree or 360 degree. Because of which you have this conformational isomerism. Now, this conformational isomerism is further classified into two types. One is geometrical isomerism, the other one is optical isomerism. So, this conformational isomerism is further classified into geometrical isomerism and optical isomerism. Optical isomerism. So, this double bond, this wherever in compounds which shows conformational isomerism, if double bond is present, then that can give rise to geometrical isomerism. Okay, you have to remember this. For geometrical isomerism, what is must? There are two conditions that you have to remember properly. Okay, so let's discuss about geometrical isomerism now. Geometrical isomerism. Geometrical isomerism. Now, in case of geometrical isomerism, you have to remember the condition for geometrical isomerism. Okay, and this is a very important question that comes in your class 11 level. Condition for geometrical isomerism. Now, there are two main conditions for a compound to show geometrical isomerism. Number one is presence of double bond. Presence of double bond. Another one is the same group should not be attached to the same carbon atom. Okay. Now, with example, to be more clarifying. So, there must be two different atoms or groups attached to each carbon atom of the double bond. So there must be two different groups attached to each carbon atom of the double bond. So let me give you an example for both this. First one, you already know it. There has to be presence of double bond for a compound to show geometrical isomerism. The second point is, now suppose you have group A here and say group A, and here say A and B. Now you can see in this compound, this group A is attached to this carbon, and again the same group A is attached to this carbon atom. Now, such compounds will not show geometrical isomerism. Please remember this. If the same group is attached to the same carbon atom, then such compounds will not be showing geometrical isomerism. For a compound to show geometrical isomerism, there has to be different group attached to each carbon atom, like group A and say group B. Here also you can see this carbon is attached to group A and group B. Now this compound will show geometrical isomerism. Let me give you an example. Here C double bond C is present. Suppose you have hydrogen attached to this carbon and say CH2. And here again you have hydrogen and here CH2. Now this you can see in this compound hydrogen and CH2. These two are different groups which is attached to this carbon, and here also hydrogen and CH3 which is attached to this carbon. These are different groups. Now this compound is also geometrical isomerism. Okay, so you have to remember different groups to be attached to the same carbon atom. Now let's discuss about types of geometrical isomerism. Let's take this example. Here you can see there are two different groups attached to this carbon atom. Now, whenever you see the molecular weight wise, okay, so if you see the molecular weight of CS3 is obviously higher than that of hydrogen, therefore this one gets more priority, say 1, and obviously this has to get now 2. Similarly here, CS3 is having more molecular weight, higher priority 1, and hydrogen is 2. Now in this particular compound, you can see that the more priority group 1 is lying on the same side of the double bond. Double bond is present here, and this higher priority group, that is 1 CS3 1, they are lying on the same side of the double bond. Now whenever such cases arises, then such geometrical isomers are known as what? Such geometrical isomers are known as cis isomers. This is cis isomer. Now, if it is the other way, then suppose you have hydrogen here and here CS3. Now here you have CS3 and here you have hydrogen. Now in this case, you can see that this is more priority group 1. This is 2, and in this case, this is more priority group, then comes 2. Now in this compound, you can see the more priority groups, they are not lying on the same side. One is lying below the other one is lying the other side of this double bond. Now such isomers, where you have this more priority group lying, so you can say diagonally to each other, or the less priority group lying diagonally to each other, then such geometrical isomers are known as what? Trans isomers. Trans isomers. Isomers. Okay, so this is very important, and you have to always remember that the trans isomers is always more stable. The trans isomer is more stable than this isomer. And in most of the cases, its dipole moment will be 0 or less than that of cis isomers. So these are the points that you have to remember from this geometrical isomers. Now let's move on to optical isomerism. Optical isomerism. Optical isomerism. Now the term itself tells us optics. Optics means this is related to what? Light. So optical isomers. Before understanding what is optical isomerism, we have to know that they are about monochromatic plane polarized light. So whenever you have a source, and from a source, if a beam of light comes, then that means it is having wavelength of it contains wavelength of different magnitude, and it is spreading in all the directions. So for the purpose of optical activity, what we need is monochromatic light. Monochromatic light means here monochromatic and plane polarized light. What does it mean? It means that they have this light which has wavelength of same magnitude, and they vibrate in only one plane. That only in one plane. Okay. So whenever monochromatic light is passed through such an organic compound, then if this organic compound rotates the plane of this polarized light, then this compound is said to be optically active. Very simple. Monochromatic plane polarized light is passed through this organic compound kept in such a container, say polar emitter. Here we call it as what? Polar emitter. Whenever this plane polarized light is passed through this container, which contains organic compound, if the light passes undeflected, that means this compound is optically inactive. It's what? Optically inactive, because it does not interfere with the path of the light. Now, on the other hand, if this organic compound, whenever this plane polarized light is passed through this polar emitter containing this organic compound, and if you find there is deflection in the direction of the light, okay? If there is deflection, please remember, if there is deflection, that means this compound is what? Optically active. So, for more clarity, you have this optical activity and optical isomerism on page number 12.42. Please go through it. And also in 12.42 and 12.43. Now, let's discuss about types of optical isomerism based on whether the deflection is towards the left hand side or towards the right hand side. So whenever there is deflection, optical isomerism, I told you what is optical isomerism. If the plane of polarized light is deflected towards left hand side, then such compounds are known as what? See, left means it starts with L, left, so they are known as rotatory compounds. So if there is deflection of this polarized light toward the left hand side, then they are known as levirotatory. If it is towards right hand side, if it is towards right hand side, then it is known as dextrorotatory. Very simple. Whenever you are confused, so left, it starts with L, so levirotatory, then there is only one possibility towards the right hand side, and that has to be dextrorotatory. So remember this much. Now, from this particular section of optical activity, you have to learn about the specific rotation also. So, specific rotation, definition, and a numerical is always expected from this particular topic. Okay. Now we are going to discuss about specific rotation, and this is also under optical isomerism. We are going to discuss about the specific rotation. The specific rotation. So specific rotation. So specific rotation is given by this expression. Rotation is given by this expression. Here, rotation in degrees. Observed rotation in degrees. Observed rotation in degrees divided by length of polarity. And this length has to be in decimeter. Please remember this decimeter part, okay? Whatever, whether it is given in millimeter or centimeter or meter, whatever, you need to convert it into decimeter. Please remember that. And into concentration. Concentration of the solution, and it has to be in gram per milliliter. Here also you have to remember, length has to be in decimeter and concentration has to be in gram per milliliter. So From this expression, you will be getting a numerical, and on page number 12.43, you have some solved numericals. It's very simple. Out of these 4 quantities, 3 will be given. The 4th one you can easily calculate. Please go through the numerical problems which has been solved on page number 12.43 and try to solve the next 3 problems which is given on page number 12.44.